It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, on today's show we switched gears from working with equations, we were working with statements of equality, to working with inequalities, are less than and greater than statements. So we switched gears from working with equations to inequalities. So determine if x equals 3 is a solution to this linear equation. It's an equation because it's got that equal sign there. Justify your decision. Well, how do we check that 3 is a solution? Well, let's plug it in. 8 times 3 minus 6 times 3 minus 2 equals 20 minus 2 times 3. Plug each side into a calculator or quickly do some arithmetic. 24 minus 6 is 18 minus... Does 18 equal 14? No, this is false, so x equals 3 is not a solution. Why? This is a false statement. That is not true. So to check if something's a solution to an equation, remember, all we have to do is plug in that value. Now I ask you to determine if x equals 3 is a solution to this linear inequality. Well, it's an inequality because it's a statement that says greater than. Notice this is exactly what we have above. If I plug in a 3, this is basically the same except I change the equal to a greater than sign. So I get 18 is greater than 14. But wait a minute, this is a true statement. So this tells me x equals 3 is a solution. Why? Because I know 18 doesn't equal 14, but 18 is greater than 14, so it's true. It is a true statement that 18 is greater than 14. So consider the linear inequality x is greater than or equal to 6. So something is greater than or equal to 6. Give me 5 numbers that work there. Well, 7, 8. Well, doesn't 6 work? 6 is greater than or equal to, because that's the equal to piece. 9, 10, 11, right? I can keep going, but 7.5 works. 9.321 works. Those are all numbers greater than 6. 6.000001 works. So if I was to graph all of these numbers here, because I can equal 6, because I'm including, I have that or equal to piece, we're going to put a closed circle at 6 to say it's part of the solution set. It's one of the possible answers. And then here's 7, 8, 9, 10, 6. Notice it's every single number to the right of 6. So what we do is we shade it in and draw a ray. So we include 6, 6 is included, and then any number bigger than it, we're going to go to the right. Notice that all the numbers to the left of it are not in the solution set. So any number bigger than 6 is in the solution set. Because I had that equal to, 6 is a solution, 6 is greater than or equal to 6 is true, it gets a closed circle. What about the inequality something is less than -2? Well, -3, -4, -5, -6, blah, 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 right? Is -2? No, -2 does not make a true statement. But -2.000001 works, so I need to get really close to -2, but I can't touch it. So graphically, we're going to put an open circle there. We're going to put an open circle there. And then notice which row am I shading? -5, -6, everything is to the left of that circle, so I'm going to shade this way. Less than, I'm going less than that point. I can get really close to -2 here, but I can't touch it. That's what that open circle means. Notice there's no equality in that inequality, whereas here that we did have that or equal to piece. For each of the following inequalities, graph the solution set. So let's look at this first one here. X is greater than -1. So the only number I really care about is -1. I like to go up 2 and then down 2. And then it's kind of 2 steps. What type of circle am I going to use? Well, can I include -1? Is -1 greater than -1? No, it is open circle. I have an open circle there because it's not included. Then I need to say which way am I shading. I want to be bigger than -1. Well, bigger than -1 is to the right. And that's my graph. State two values in the solution set, 0, 1. Those are integers. Some non-integers would be like 1/2, 1.273, I don't know. There's lots of integer. These are non-integer answers. But you just need to state 2. Notice that there's infinitely many choices. You can keep on answering the question. There's no end to answering that question. X is less than or equal to 7. So here's 7, 8, 9, 6, and 5. 7, notice, is going to be getting a closed circle. It's going to get a closed circle because I have that equal to. 7 is part of the solution set here. And I want smaller than 7, so I'm going to shade to the left. Notice it follows the way the inequality is pointing. I'm going to go to the left there. So I have a closed circle, and I'm going smaller than 7. These next two are a little weird because x isn't in the front seat. This statement here says 2 is less than x. Well, we can flip this entire inequality around by reading it backwards. X is bigger than 2. That's really what this is saying. X is greater than 2. If 2 is smaller than x, who's bigger? X is bigger than 2. So we can graph that. 2 gets an open circle. 3, 4. Make sure you're numbering these and not just putting one number on a number line. That's not helpful. And I want to be bigger. There's my open circle. I want to be bigger than 2. I want to go to the right. Last one here. 5 is greater than or equal to x. 5 is bigger than x, so x is less than or equal to 5. I'm flipping that entire inequality around there. So I make my number line. 5 is going to go in the middle. 6, 7, 4, 3. So 5 is getting a closed circle because 5 is a solution to that inequality. It is in the solution set, and I'm shading less than. I'm going less than 5. That away. Not too terrible, was this? So 5 and 6 are questions that they ask a lot on the Regents exam as follow-ups of what's the smallest integer or what's the biggest integer. And here's how this kind of works. X is greater than or equal to 3. Let's graph it so I can look at this. Closed circle, and I'm bigger than 3, so this way. I'm bigger than 3. I'm shading to the right. What's the smallest integer? How low can I go? Well, 3. 3 is the smallest, because I can be 3. Let's jump down to 6 here. State the largest integer. So x is less than or equal to 8. 9, 10, 7, 6. So 8, notice here, is going to be getting an open circle. 8 is not part of the solution set, and I want to be less than it. So anything that I shaded is in my solution set. I want to know what's the biggest integer. Well, 8 is not a solution, so what's the next biggest integer? 7. 7's not the biggest number. There's like 7.5, 7.9, 7.99999, but 7 is the largest integer value. So take a second, draw these other 4, and answer the question, what's the smallest and what's the largest? So here's what I got. X is bigger than 4. 4 gets an open circle, and I'm shading to the right because I'm greater than that. So what's the smallest integer? How low can I go? Can't go to 4, so we've got to go to 5. I don't like the way that looks there, so I'm going to say x. -1 is smaller than x. X is bigger than -1. Let me draw my number line. -1, 0, -2. Notice I'm going to have an open circle, and I'm going bigger than -1. What's the smallest integer? It's not -1, so it's got to be 0. 0 is the next smallest integer in line. So you have to be careful when there's an open circle, because you can't use that starting number there. 2 is greater than or equal to x, so x is less than or equal to 2. Here's 2. Close circle. And I want to be smaller than it. What's the biggest value in that ray there? The biggest integer? 2. I can be 2, so 2 is the biggest value. Over here, I've got -5, -4, -6. I got a closed circle again, and I'm shading x is less than that. Shade this way. What's the biggest number? -5. It's easy when there's that equal to piece because it's just that number. Otherwise, you've got some thinking to do. So we had our properties of equality. Let's see how that works with inequalities. We all know that 4 is less than 8. That is a true statement. That is clearly a true statement. What if I add 3 to both sides? 7 is less than 11. That's still true. What if I subtract 4? 0 is less than 4. That's true. Great. We can add and subtract and we're all good. What if I multiply both sides by 2? 8 is less than 16. True. So that worked. Multiply by 2, divide by 4. 1 is less than 2. That is, again, a true statement. So it looks like we can divide and multiply. What if I multiply by -2? If I multiply by -2, that gives me -8 is less than -16. This is a false statement. To fix this, I'd have to say -8 is bigger than -16. Notice the sign changed. I needed to flip the sign to make it true. This was false, so I had to flip the sign. What if I divide by -4? -1 is bigger than -2. Again, this is a false statement. I need to flip that sign to make it true. So, the addition property of equality, same thing. The addition property, we can add, subtract, good to go. Adding and subtracting does not change the solution set. Multiplying and dividing, though, we got a warning. We need to be careful for working with negative numbers. If we divide or multiply by a negative number, the sign changes, the sign flips, the inequality flips. If you have a less than sign, it becomes a greater than sign. If you have a greater than sign, it becomes a less than sign. So be careful when we work with inequalities. If you divide or multiply by a negative number, the sign changes. Let's solve these two to put that skill to test here. Let's test that skill out. So isolate x. So 8x minus 6. Well, clearly we're going to add 6 to both sides. 8x is bigger than or equal to 16. Divide by 8, we're all good here. X is greater than or equal to 2. Excellent. We solved the inequality. X is bigger than or equal to 2. Over here, it looks like I'm going to have to subtract 16 first. -4x is bigger than 16. I'm going to divide by -4. Warning. I'm dividing by a negative number. You need to be careful. I get -4 over here, but my greater than sign becomes a less than sign. X is less than -4. Whenever we divide or multiply by a negative number with linear inequality, or actually any inequality, we need to change that sign to keep the truth value. Otherwise, we're making a true statement false. And in the next lesson, we practice solving for the entire day. See you then.